Bird stuff happens in a highly important context. That allows me to rank all these behaviors, right? So that ranking is really cool, right? So I can score all these behaviors. I know what's more important compared to what's less important. Okay? Now I can do some further math on it. The second further math I can do on it is now I can look for contributions of these behavior risks onto entities in common, right? I want to be able to take multiple behaviors and collapse them on things that are doing those behaviors over and over again. And this is actually how we reduce the noise. This is how we reduce false positives. And I got motivated this way. Let's suppose that we just see John compromised. Again, name change to protect the ASIC. Suppose we saw some guy's account, and he just accessed a network share that's unusual for him. Never touched it before, and it's not associated with anything that he or his team should be touching. Okay? We can give it a number. Maybe it's a 25. It could be really important. But let's face it could also be a false positive, right? Maybe he just changed jobs. He moved from one group to another group, and it's actually okay for him to be touching this network share for the first time, right? But suppose he also just did it at 2 in the morning, and we've never seen this account do anything at 2 in the morning before. And suppose he also just accessed a large amount of source code from something that had been inactive for months. And suppose he copied all those source code files to a cloud service that no one else has been using, and so on and so forth. So your intuition here should be that the more of these behaviors coincide on the same thing, John in this case, the less it starts to feel like a false positive, the more it starts to smell like something that should demand someone's attention, and it's worthy of investigation. Does that make sense? Okay, cool. So the idea here is you want to be able to gather evidence together so that you have a single, what we call a story, around something that demands attention by the security team. And the way you can do that is very simple. We have all these logs, we have all these data sets, and essentially what we do is we do feature extraction on top of these data sets. Right? Different data sets have different semantics, they have different features that are relevant. Let's suppose that we have a single data set, we have a couple features, there might be more, it doesn't matter. In practice, we have about 20 to 30 features per data set. So if you have 3 data sets that are being analyzed, we've got about 90 features that we're drawing from. And then you do anomaly detection and other models on top of those features. That's the first layer, right? So we've got all these behavior scores. And then you want to sort of combine them together in some meaningful way in order to compute the total aggregate score, right? And so that does a great job, right? It works fantastically well to be able to take the billions of events that we have on this side and compress it down to dozens of things to investigate. We regularly in practice, we have a number of customers that are ingesting literally terabytes of data a day. Right? It's crazy, right? But we can take billions of events and turn it into just dozens of stories for their team to investigate. And each one of those dozens are, because they're waiting for mounting evidence, are worth their time. Right? And that's really cool. Yes, sir.
So I have a question about the customization of the features. It seems that it's a function of the business, right? So you have to be involved with the business itself, so that they tell you it's a lot of headache, right?
Yes. Okay. So I'm going to try not turn this into a product pitch, but you're exactly right. There's a lot of value in customization. There are security products out there that will help you classify your data. For example, you can say this is my confidential stuff, this is my non-confidential stuff, and we do have these guys are on a watch list, these guys are not, right? So that information is valuable. We do have an API in our product that incorporates that information, but for us, it was very important to not require any of that data, right? So in the absence of classification information, we basically treat every entity equally, and we focus primarily on the behaviors. And that's really important because you want to be able to install a system and have it produce meaningful results right away. You don't want to require a fully classified data environment. No one has that. That does not exist. It's hard to do. It takes a long time. And you don't want to require months of fine-tuning and customization. Right? So I'll just go through really quickly. This is someone, he logged in and mistyped his password 30 times on this machine. Right? That's not because I specified a rule, hey, tell me when someone typed in more than 29 password failures. Right? We learned that for this guy on this machine to mistype his password 30 times, that is this weird. And that's why it's at the top. The second sentence actually comes from Active Directory. This guy has successfully logged into this machine, but he never does that. That's really weird. right? So that's why it's so high risk. Taking more than normal, more compared to others, this is a good example of the correlation stuff, right? So these things will be weighted a certain way. White is normal, red is just what happens, so it's very easy to understand what's going on there. These 3 projects were inactive, no one else was touching them. Running CalNet and PSexec, security guys in the room, you know what's going on here, right? But this is not false positive. This guy's not a sysadmin. He never runs these executables, but all of a sudden he is, right? So painting a really clean single picture of someone that's probing around, doing some recon, doing some lateral movement out of a source of intellectual property in advance of some staging, possibly just before an exfiltration, all done 100% using machine learning and anomaly models with a single score. And that's how our product works. I can't claim to be a data science company without actually talking about how we do it. So this is how we do it. So we do have a data science team. We also have a data engineering team. And what we do is we spend the data science team doing data stuff, right, and exploratory data analysis, and basically they output math. And then the math gets handed over from our data science team to the data engineering team to put the math into motion, right? And there are special skills that happen at each step of the way. I'm just going to sort of drill into exactly how we do what we do really quickly, because you guys, honestly, you can do this all yourself, right? You don't need us. We do a lot of stuff with open source. We actually contribute to a lot of open source libraries as well, so we're pretty involved with that community. But on the data science side, we do exploratory data analysis, right? Data science guys know that this is not a term that we made up, this is a data science term. We spend a lot of time working with customers and prospective customers to get their data, right? Because you can't do data science on theoretical or simulated data. It just does not work, right? So we basically interview them, we understand their use cases. We want at least 30 days of historical real data. We find that that's a good combination. We understand their use case, we understand the semantics of the data set, and then we'll do some math in R, right? We have a growing catalog of models that we have. We try those, we retune it, we build and invent new math, new models, and then we present the results back to our stakeholders. We say, does this work? Did this catch the guy that you knew about? Did this surface bad guys that you didn't know about? And that happens a lot. But basically, it's entirely an exercise in generating math, okay? And then what we do is we take that math and we hand it over and put it into production. This can be quite hard. Remember, petabytes, terabytes a day, right? It's one thing to write down a set of equations on a chalkboard. It is a completely different thing to run that set of equations at scale and in real time. It is really hard, right? Luckily, there are all these companies that do this for a living. LinkedIn gave us Kafka, right? So I've got a message bus that can now process 1 million events per second on a single commodity box. That's amazing, right? By the way, LinkedIn, I think they're now processing 1.3 trillion events per day. That's cool. Spark, Phoenix, HBase, Elasticsearch, Kibana, these are all technologies that if you looked in the space a little bit, they're all open source. They all came from companies like LinkedIn, Facebook, Google. They all scale fantastically well. They were made to do math at scale. And so we chose those tools. We have both real-time and batch models. I think I'll actually show you how we implemented the system to be able to do that. Yes, sir.
Question on the 30-day cycle. That may work for some firms, but with people who have like product release cycles and like, where there are different behaviors, for those sorts of companies, do you essentially look for that extra data?
Yeah, sometimes. With the larger companies, they actually have a data retention policy that sometimes we run into as well, right? So they can't hold on to the data for too long. And then we get the complete opposite. I have one bank that, believe it or not, they've been collecting, they have almost 20 years worth of internet data. I didn't realize the internet was around for 20 years, but they have all this data. I'm like, do you want some data? Too much. But yeah, it varies a lot. The thing to realize though is our product is entirely out of the box. Like, we don't typically do data science for a customer. So they'll buy a product. We know we've already done all the stuff for Active Directory. We've already done the stuff for SharePoint. Like, we've done all the basic stuff, right? So they'll connect us. We only need to go through this cycle if there's a new data source that we want to bring to our product and to give to our customers. This makes total sense once you sort of know what these pieces do. But I want to share it with you because it actually took us about a year to sort of figure this out. So I thought it might be useful. So we got all this data. We got some data that's coming in real time. We got some data that's coming in batch, right? In our case, at least, sometimes our data is analyzed in the cloud, in our hosted system, sometimes it's on-prem. When it's in the cloud, S3 is a great place to cache that data, right? So we have these things called connectors, which basically sift the data. The data in a typical environment requires I/O access to the file or to the port that contains the data. There's a technology called Flume, which is really good at moving large amounts of data from one place to another. It was built for that. It's horizontally scalable. What's it called? Logstash. Logstash is another one that would work equally well. So you can move the data in, we dump it onto the bus. So this is that Kafka bus that came from LinkedIn. So we take the events, we dump it onto Kafka, and at that point, the data takes a fork. We do both real-time and batch analytics, and this is important. The secret to making machine learning models run in real time is to split it up, right? Because you want the model building to run in batch, and you want the model scoring to run in real time, right? Does that make sense? When you're building a model, you typically require a large amount of data. You know, give me the history for this account for the entire year and update my baselines, right? Sometimes you can do incremental training, but in general, you know, it's a batch operation, right? So basically, we run that in a big loop, right? Because it's a big operation. So we're talking MapReduce, we're talking Hadoop. In our case, we do batch on this side of the equation, right? So we've got HDFS. We use HBase on top of HDFS, which basically makes Hadoop data look like a database. And then we use Phoenix on top of HBase, which lets us run SQL on top of large amounts of data, right? So that's a batch stack. Right? So this is what it's learning, it's doing the validation, it's building new baselines, it's getting smarter and smarter as more data comes in. So that's the batch side. Now the fork is to be able to take every event that's also coming in and being able to instantly give a score to that behavior. That's a real-time operation. We want to be able to catch the bad guys the millisecond they do something bad. So that's scoring. The good news about scoring is that's a constant time operation, right? You load the model, you run it through the math, you spit a number out at the end. So we do that using Spark, which is a great real-time, in-memory processing engine. It's also very scalable. It's super fast. So basically, we store our models. We continually refine the models and improve the models in batch, but we always load the latest models in Spark. We just compute in real time, and it works fantastic. All of our results, we dump onto Elasticsearch. It's like a Google for your own private data. So it's a very horizontally scalable search engine. When you think of search, you typically think of running a query and then pulling in the results. But guess what? That query API works fantastically well to power a UI as well, right? If I can instantly look up in login time any risk score for any account, for any machine at any given point in time, then I could build a fantastic, very responsive UI. And that's how we've done this, right? So this system is basically the core of what we've done here. Okay? Yes, sir?
Just a quick question. In order to make the analytics part adaptable for the constant change on the front end of data stream, there needs to be a feedback path somewhere so that essentially the analytic box can evolve. Do you take the results from the analytics, or do you take the final reports to feed it back?
Okay, that's a good question. There are three ways in which we do feedback. Two is in our in-market solution today. Again, I hate sounding like a commercial, but there's a third one that's also coming. So the way people tune the system today is those weights that it described on the different use cases and on the entities, they actually can tune them, right? So they actually can provide information saying, hey, this guy is on a watch list, I want you to watch him more closely. This file is super important, I want you to watch that more closely, and that can impact the model. They can also tune the various models that we have. They can say, for us, for some guy to use Dropbox and a USB key, it is the worst thing in the world because everyone should know that that's against policy. So that feedback exists. The third thing that's coming that we're actually building in now, it's really cool. Basically, we wanted to give the analysts, the users that are using our software, the ability to have a thumbs up, thumbs down button, right? And it's kind of like how on Facebook, when you say more like this, it will find more like that, right? So that provides a really easy UI gesture that provides feedback so we can learn too. And we worked out that. It's
my
really
second
cool.
question
Yeah,
is, how do you handle soft data,
yes.
human analytics?
Yes.
It goes like yes, no, and how do you quantify them?
Yeah, so we are doing basically human in the loop in that case, right? And that's something that we figured out the math, we're just working out the UI. That's coming up. Yes?
Well, collecting more data about people and employees is important to catch the bad guys, but what about the good guys, is there any concerns for privacy on the data and the information, especially that it's going to the cloud at some point?
That's a perfect question. Hold that question. I'm going to answer that in 2 slides.
Okay.
All right. The stack, this approach, it works really well, I gotta say. So I'm gonna tell you some stories. So here's one story. This is one of 4 stories that I'll share with you. This happened about a year and a half ago now, but it was great. It's still one of my favorite stories. There's a large semiconductor company. They make chips for mobile devices. They're based out of the States. They're in a warm. Actually, I should tell you too much more. But if you have a cell phone, you probably have their chips inside that cell phone. They became aware of 2 of the engineers that stole chip firmware code from them, and it was a big deal. They actually went to the news, and they wanted to see if they could analyze the source code files that showed people checking in and checking out source code files to see if they could use just that data source to detect and prevent that from ever happening again. They worked with a very large company, not us. They spent $1 million a year. That effort failed. But after deploying our models and our solution within 2 weeks, not only did we find the 2 engineers that they knew about, we found 11 additional names that they did not know about. All 11 were stealing. 8 of them were comprehensive accounts located in China. It was a really big deal for them, and we were very happy. This is the data set.
Of course.
This is what it looks like.
Should we add that?
And I'm going to read it out for you. I'm just kidding. The first column is actually the timestamp. Okay. The second column is actually the name of the engineer. Now, back to your question. So we do deploy both in the cloud and on-premise. So the people that are really regulated and really secure, they will always insist on putting it on-premise. But when we sell to European customers with Workmen's Council concerns, when we deal with some companies that have PII concerns, we make sure that every one of our connector, which is how you feed data into our system, has anonymization built in. So we take everything that is a name or some sort of path information that could be sensitive, and we do run it through a one-way hash. So the reason these names don't actually look like names is because we've run it through that one-way hash. Math doesn't care if it's John Smith or ED78. It works perfectly fine as long as it's uniquely identified correctly, it's same consistently across all the data sets. And that helps a lot, and that's how we were able to sell into Europe. The next column is the IP address. There are 2 more columns there. The action, this is literally what the engineer just did in their source code system, whether they synced or diffed or printed. And the second is actually the file and folder name. In this case, also anonymized that they hashed. Again, math doesn't care. We just need a unique string. So I want to show you the data set because this is a little bit different than some of the data sets that we get in data science, right? In our world, we get really skinny, tall data sets. We don't have really fat data sets, right? So we don't have to do dimensionality reduction or anything like that. If anything, we're trying to build more features on top of that. But if you look at this pattern, that's very typical, right? To have a timestamp, some sort of identifier, some sort of action, and some sort of target for that action, that's not just in source code. That's in network traffic, that's in SharePoint, that's in file shares, and so on. And if you look at these 5 columns of data, and you had to take a guess as to how many models you can build, you might be surprised that we were able to build, I think we're up to 27 models now, just on those columns. They're all really great. I'm not listing all 27 of them here. I'm actually going to show you 2 of them. But I want to show you the categories that we labeled them. So we wanted really easy to understand models. So we didn't want to give them fancy math terms, but we have models that we call sneaking models. That's when you're doing something outside your normal behavioral pattern. You're sneaking around at 2 in the morning, doing something at your time. Hoarding, that's when you're taking a lot of stuff in a short period of time, or maybe taking small bits of stuff over a long period of time, trying to go low and slow, as I said before. We have models that work for that. Mooching is really cool. We found that for many intellectual property repositories like SharePoint, if you measure how much an individual contributes to that repository and divide that by how much they take from that repository, that ratio is actually highly predictable. It varies from role to role, but it's a very interesting ratio. So we have about 4 or 5 models that key off of dangerous changes to that ratio. Wandering is when you're accessing a type or section of intellectual property that we did not expect. So, fairly intuitive labels, fairly simple. Let's try and figure out when it's normal for someone to be performing some sort of activity, like accessing source code at any given time. This is real data from that customer. So if you just focus on the x-axis at first, what you see here are the 24 hours of the day. And this is a KDE, which half of you guys will already know, but I'll just bear with me for a second. So I want you to imagine that whenever this guy touches source code, I'm going to draw a little tick at the time that he did that. So this guy comes into work, starts working with source code, tick, 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 tick. He takes a break for lunch. That's why you see this white gap, no ticks around noon. Then comes back again, tick, 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 tick. Goes home at around 3:30. Clearly works at Interset because he gets back on the works back at 8 o'clock, works until almost midnight before dropping to sleep. Good guy. When you do a KDE, you're basically dropping little Gaussian kernels, right? And they sum up in a very predictable way. And what you get here is a curve that basically tells me roughly how probable it is for this person to be active at any given time of day. If I see this guy, if I see this account doing something with source code at 10 in the morning, that's normal. Always does that. If I see him doing something at 12 o'clock, well, that's okay. About 40% of the time he works through lunch, right? But if I see this account doing something at 2 in the morning, that's worth paying attention to. Never does that, right? Make sense? It is amazing how even this simple technique is so interesting. There's almost like a fingerprint for every single human for certain behaviors. Here are two engineers from this company, engineer number 1, engineer number 2. And we're now looking at the days of the week. So that's why you see all these humps. Look at engineer number 1. This guy deserves a raise. He is working 6 days a week, right? And in fact, the way he works on a Saturday is almost exactly the same as Monday, Tuesday, Wednesday, Thursday, and Friday. Right? That's great. This guy actually turned out to be a contractor at this company, and it kind of shows, right? Monday to Friday, doesn't work as hard. Maybe he works extra hard on Thursdays because there's a sprint planning meeting and demo on the Friday. So kind of a different character. Right? In fact, if I take those same two guys and I zoom in on the hours of the day, hardworking guy. Look at this guy. Wow. Starts super early, works past midnight. Completely different than this contractor. 9 to 5. There's no question this guy's out at lunch. Right? He is not working at lunch. Maybe once he worked past 8 o'clock, but come on, different guy. But anyway, so imagine being able to do that at scale on the 20,000 employees at this particular company. So that's one model. Here's the second model. This one's a little bit cooler. What we did here is we took all the access patterns for all the engineers, and we across all of these source code projects, and we just basically clustered it. Okay. So every node here represents a different source code project. Every edge represents a different set of engineers. The length of the edge, we set it to basically how normal it is for that set of engineers to be accessing the two source code projects that are connected to the edge. Does that make sense? Okay. So basically, when you run that through a cluster, what you end up with is an understanding of the typical patterns of access across all the engineers, across all the source code projects. And they ended up corresponding exactly to 4 software teams at this company. Right? No one told us there were so many software teams, but we discovered it mathematically. Right? So there's a fairly small software team in the purple, small because it's only made up of 2 source code projects. On the other hand, there's a fairly large team in the green, made up of 22 source code projects. Right? And the fact that even this 2D projection shows that these clusters are so tightly packed together and separated, that's a nice result, right? Because that tells me I have a really predictable model. In other words, if I'm an engineer on Team Green, then it is perfectly normal for me to access any other green source code project, right? Because look how, it's almost like a clique, right? It's so tightly packed together. On the other hand, if I'm an engineer in Project Green, and I reach out and I take source code from Project Red, then that is quantified in my model. So this guy was on Project Green. He did take source code on Project Red. Did it at 2 in the morning. Never saw him do anything at 2 in the morning before. And he also took 16,000 files at 76 per hour. And that's how we found him at the 11 guys. This was a, this is a scary one. So this was a VP of engineering that worked at a US-based military contractor that makes drones for the US Army. And this VP of engineering came in on a weekend and went to YouTube, played Pink Floyd, which is perfectly fine. But then he proceeded to copy literally thousands of PowerPoint slides onto a USB drive. That instantly spiked in our system, and the security team worked with HR, and they were able to intercept him before he was able to leave the building with a hard drive. So that was really great for us. This is a pharmaceutical company This was sysadmin who, think back to my first example, who actually took large numbers of process documents and mailed it to her home Gmail account in order to bring that with her to a job at a competitive company. And she was detected and was processed. This is a cool one. This is a media company. They're in the movie and entertainment business.
My email anymore.
Not Sony Pictures, I just want to be clear, not Sony Pictures. But they use a cloud sharing system to share trailers and scripts and things with third parties, right? And they're a multinational company, and there was an employee that I believe was based in Germany and traveled to the UK quite a bit. And one model was seeing a bunch of new devices show up on an IP address that was associated with the States. That's anomaly number one. Anomaly number two was everything that was done by the US-based IP address was a take, right? So they were downloading, they were zipping it up and syncing down. There was no contribution back, which is unusual, right? Usually when you share something in Dropbox, someone edits it, someone comments on it. In addition, everything that was downloaded by the US-based address had a high age. When you think about collaboration systems, it's normal for the delta between touches to be short, right? I'll upload a document, then someone else will download it, then someone else will comment on it, right? There's actually a curve that I could draw on the time differences between touches. And everything that was downloaded was old from the US. And basically, her account was hacked. We now have a bunch of customers, and I'm almost done. We have a bunch of customers. I'm not going to tell the slide, but what these guys all have in common is they all have data that they want to protect. What's not on the slide, but what I believe I'm now legally able to share with you now, is that we also have multiple intelligence agencies using our software, both in Canada and in the States. And I think we're just getting the press release ready, so we're really excited about that. It's a great Canadian success story. We are the largest deployed software in the IC community in the States, and that is, I think, really cool, especially since it started out in Bell's Farmers. Okay, I'm done. 2 Kung Fu moves. Get the data right, get the math right, it will do wonders, and thank you so much for your time.